In our fish tank laser experiment, the first thing I pointed out was how the bottom of our fish tank in our refracted image appears so much higher than it does in our control image. To that, a member of our debate board by the name of Jeffrey Pinion asked, "Why don't we see the horizon gradually change positions?" With that, I had to share with him the Skunk Bay horizon observations, where you can clearly see the buildings, the hills, and the mountain in the very back there appearing to move up and down in this time-lapsed footage. Please notice how the mountain here appears to have sunk behind this hill, just like a boat out on the horizon. The Earth isn't suddenly becoming more curved and less curved here. That is refraction taking place. Alright, now last time we talked about how we have two rivaling claims. On the flat Earth, we claim that refraction limits our range of view, and how when there is less refraction in the air, that extends our range of view. On the other hand, on the globe Earth, they claim that refraction extends our range of view, and lack of refraction limits our range of view. Recently I was chatting with a guy by the name of Bobby Shafto, and he didn't seem to understand what that meant, so I told him I would illustrate it for him. So here we have a guy with an unrefracted view that is parallel to the Earth. Now, pretending atmospheric opacity didn't exist, without any obstacles in the air, with that kind of view, he should be able to see on forever. If he had supreme telescopic vision, that is. Now, if we refract that light downward, he can no longer see on forever because his range of vision hits the ground. And yes, this does cause the ground to appear higher than it was before, just like we observed in our fish tank experiment. And because of the density gradient, there is more refraction at the bottom than there is at the top. That creates our sinking boat effect. Please notice how the bottom of our sail appears to be touching the surface of the water in our refracted image, whereas that is not the case in our control image. I get too many people who ignore that fact. So that's how it works on the flat Earth model. Now on a globe Earth model, if there were no refraction, you would not be able to see infinitely far across the surface of the Earth, because the Earth curves out from under you and goes out of sight. But if we were to apply atmospheric refraction to the globe Earth, that would allow us to see around the curvature of the Earth and extend our range of vision across the surface of the Earth. I hope that makes sense to you. So what is going on over here? We can see some definite refraction taking place. Is it extending our range of view like the globe Earth model claims? Or is it limiting our range of view like the flat Earth model claims? Well, here in our top image, I can see a lot more of the mountain, and there's a lot less distortion. Just look at how clear and crisp all the trees on that little peninsula are. In the bottom image, however, those trees look really compressed. It even looks like someone went and chopped them down or something. Alright, so in our more refracted image on the bottom here, our range of vision is more limited, just as our flat Earth model predicted. Thus, I claim victory for the flat Earth. Thank you for watching. If there is something I have said that you disagree with, please come and participate on our debate board. It is totally free and web-based, so you don't have to download anything. There's a link in this video's description.